Okay, so today we're going to continue on talking more about atomic structure and some of the key experiments that led to the formulation of quantum theory and the theory of electronic structure. Before I start, for those of you that celebrate it, Happy Lunar New Year. Junimen Shenyan Kwaila. That's the only other language I know it in, sorry. But anyway, enjoy that if you celebrate that tonight. But we're going to, for now, talk about chemistry, which hopefully is just as enjoyable as celebrating the New Year. So we're talking about Bohr Equation and quantum mechanics and continuing on with that today. Now, a little bit of warning about the next week or so. It's going to come at you pretty fast. The way this course is set up, we do a lot at the beginning. So we have to go through all the way to the end of Chapter 2 by next Friday. So Chapter 2 is going to be very fast. I probably won't have time to do as many problems in class as I would like, but I'll have the homework review videos that I'll be posting starting on Monday and once a week, so you'll have a chance to see me do more problems there if anything's missing in class. It should slow down a little bit after that, but we do have to go pretty quickly through Chapter 2 in the next week or so. All right, so where we left off last time, we talked about some observations that led to the ideas that that energy levels in matter are quantized and that the energy of electromagnetic radiation is also quantized. And we're going to talk about now a little bit about how the first atomic theory and how does this all relate to the structure of electrons in atoms. So we don't really have an atomic level picture of this just yet, but that's what we're going to get to today. All right, so the person that formulated this, Niels Bohr, his idea really came about by studying what are called atomic line spectra. So the first thing we'll do is let's talk about white light. If you see light that's coming from the light bulbs above you or the sun, it's more or less what we call white light, which has all colors of light built into it. It's a continuous spectrum, so every single wavelength, every single frequency is present in some fashion. So when you have continuous white light, you have all visible wavelengths, the whole Roy G. Biv spectrum that we talked about a little bit, but nothing's missing. And of course you've seen this in a rainbow, which is just scattered white light, where you can actually resolve all the different colors that make up that white light. So that we're familiar with. And when you take samples of elements and you excite them, and by exciting them I don't mean getting them riled up, I mean taking an electrical charge or some sort of high energy source and putting them into the atoms, you will get light that comes off of those atoms as well. So they go up to a higher energy state, and then when they come back down, when they release that excess energy, it often comes off as light. And we'll talk more about that process as we go forward. But when you do that for hydrogen, the light looks kind of white. It looks like it's fairly white light. But if you separate that with a prism, you don't see all of the colors. You don't see a continuous rainbow of light. You just see a few discrete wavelengths. And so that's what the line spectrum of hydrogen looks like. So when substances are energized, they give off light. So that's the first key point to understand about this. All right, so substances will give off light when they're energized, but for all atoms, and specifically for hydrogen, which is the one that I'm showing here and the one that Niels Bohr studied the most, only a few sharp lines are observed at discrete wavelengths. And each of these lines corresponds to a discrete wavelength. Okay, so that's what it looks like for hydrogen, and if you did for other elements, you would see different wavelengths, but still very sharp, discrete lines, not a continuous rainbow when you have light given off by a substance. So this speaks to the idea that we've already talked about, which is that the energy levels in atoms are not continuous. And so the idea that Bohr came up with to explain this is what's named after him now, the Bohr model of the atom. And so this is really the first major attempt to explain the structure of the atom. And as we'll see, there's some things about it that are wrong, but it does have some very nice features and some things that it helps us explain and predict. All right, so the Bohr model of the atom is applied mostly to the hydrogen atom. And so here's the three postulates of the Bohr model. The hydrogen atom only has certain energy levels. All right, so again, the idea that there's not a continuous ordering of energy levels in atoms, but that they're quantized in some sense. And what determines these energy levels are fixed circular orbits of the electron around the nucleus. So this is what's often referred to as the planetary model for the atom, where you have your nucleus in the center and your electron or electrons are going in regular circles around the nucleus, just like the planets orbit around the sun. So the electron goes around the nucleus. And so each of these energy levels corresponds to a different distance from the nucleus. And again, not all distances are possible, but you'll have an orbit at one radius, that's a certain energy level. You'll go out farther from the atom, from the nucleus, that's a different energy level, farther out, and so on. So that's what determines the different energy levels, is how far away the electron is from the nucleus as it orbits. So that was his idea about the energy levels. And then in terms of how this energy level changes or doesn't change, the atom's energy level does not change while the electron moves in a particular orbit. So as long as the electron stays in that orbit, the energy level does not change at all. So these are called stationary states or stable configuration, where you're not changing energy as the orbit is happening. Constant energy of the electron around the nucleus. Now the part about this that was a little bit weird and that they couldn't really explain, and this model doesn't fully explain, as it turns out, is that normally if you have a positive charge at the center and you put a negative charge and start orbiting it around it, that negative charge is going to get drawn in and crash into the nucleus in the center. So why do we have these stable orbits without the energy changing? That's a part that this model doesn't really address, but it presupposes is true, that the electron will go around in these circles forever and ever and ever, as long as there's no energy input given to the system. That's kind of weird. It kind of flies in the face of what we would normally expect for charged particles, but nonetheless, that's what has to be true for the Bohr model, and we'll see later on how that's not quite correct. Okay, and then when an electron changes to another energy level, this involves either absorbing or emitting a photon of energy, of light. Okay, so the electron, sorry, we're just talking about hydrogen here, a single electron. To some extent this applies to other atoms as well, as we'll see. But electron changes to another energy level, which again corresponds to a specific orbit of that electron about the nucleus, by absorbing or emitting a photon. Okay, so these little packets of light energy that we talked about, called photons, are always involved when you have an electron changing energy levels. So when the atom absorbs a photon, when it takes in the energy of a photon, it will jump to a higher energy level. And then when an electron is in a higher energy level and it jumps back down to a lower energy level, it's going to give off a photon as that excess energy. That's what the process of emission refers to. Okay, so then in order for this to happen, the energy of the photon that's involved, either that's absorbed or that's emitted, depending on the process you're talking about, is equal to the absolute value for the change in energy of the atom. All right, the change in energy of the atom can be positive or negative, depending on whether it's gaining or losing energy. But then that energy, that magnitude, corresponds to the energy of the photon that is either absorbed or emitted during that process. And when we talk about this delta E here, anytime you see the sign delta in chemistry, another Greek letter that we're going to have to see and learn all the time, that means final minus initial. So that's the final energy of the atom minus the initial energy of the atom. And again, by these processes, the atom can go either higher or lower in energy, so this can be either a positive or negative quantity for delta E. But photon energies are always positive. We don't have negative photon energies. Okay? So those are the postulates of the Bohr model. And then before we start drawing pictures of what this looks like and seeing some more equations, let's talk about some terminology associated with the Bohr model. So we're going to start now learning about what are called quantum numbers. So we're getting into what's called quantum theory, and we have what are called quantum numbers that dictate a lot of the ideas here. So in the Bohr model, there's only one quantum number you have to worry about, which we call n. And these quantum numbers in the Bohr model are positive integers. 1, 2, 3, so on, which are associated with the radius of the electron orbit. So I'm not going to introduce this equation, but the Bohr model derives an equation for the radius of the electron orbit, which depends on the quantum number n in some fashion. Okay, we're not going to show you that equation, but that's what the value of n determines, is how far away you are from the nucleus. So it's abbreviated, as I said, with the letter n. And the radius and the energy of that orbit depend on the value of n. And we'll give you some equations for energy in just a minute here. All right. So then we have what are called ground states and excited states. So the ground state is when n equals 1, and that's the lowest energy orbit that an atom can have. And I don't have it here, but I guess I should mention that the other term is called excited state, and that's anytime n is greater than 1. Okay. So normally, in its stable form, if you had a collection of hydrogen atoms, they would be in their n equals 1 ground state. But again, if you put energy into those hydrogen atoms, they can go up to an excited state. And then when they come back down to the ground state, that's when energy is given off. So this is an opportune time to tell probably my favorite chemistry joke, or one of my favorite chemistry jokes. So what is higher in energy, a hamburger or a steak? I guess I should say, what is lower in energy, a hamburger or a steak? A hamburger, because it's in a ground state. All right, I'll be here all week. Tip your waiters. All right, so we don't have a lot of time for jokes today. We have some really important things to do. So we're going to talk now about more in detail about the processes of absorption and emission. So as I mentioned, when an atom changes energy levels, it either absorbs or emits a photon. So absorption is the process where the atom interacts with a photon. And this interaction causes the electron to move to a higher energy state. Okay, so that means the photon energy is absorbed. That's why we call it absorption, and that absorbed energy goes to shooting the electron up to a higher energy orbit. And so in this case, the energy of the photon, of course, is equal to the change in energy for the atom, which is going to be positive. So whenever you have absorption, the atom is gaining energy, its change in energy is positive, and the photon is consumed. Emission is the opposite process. So an electron moves from a higher value of n, so from some excited state, to a lower value, either a lower excited state or to the ground state. And when this happens, a photon is generated. So the excess energy that is given off comes off as a photon. In this case, the energy of the photon is still equal to now the absolute value of the change in energy for the atom. Now when an atom goes from a higher energy state to a lower energy state, the change in energy, of course, is negative. So that you'll have two different signs for delta E depending on whether it's absorption or emission. But you calculate the energy of the photon in the same way. It's just related to the magnitude of the change in energy for the atom in that situation. All right, so those are some more terminologies. So let's draw some diagrams to hopefully clarify this even more. So as we've been talking about, this model presupposes that the electron moves in circular orbits around the nucleus, and that the quantum number n is going to determine the radius of that orbit from the nucleus. Okay, so we have, that's going to be our nucleus, in case it wasn't obvious. So our nucleus is still that very small concentrated mass of positive charge at the center. This model doesn't change that piece of the story. But then we have these circular orbits that the electron can sit in, and the ground state is going to be the one that's closest to the nucleus. That's n equals 1. And as we go further and farther away, n equals 2, n equals 3, n equals 4, n equals 5. These radii are not drawn to scale, so be aware of that. These are not to scale, but the energy levels that I have over here are. So as I also said in the description of the model, the energy levels depend on the value of n as well. So we have here an energy scale going from bottom to top, where the energy is increasing as we go from the lower to the higher. And these also depend on the value of n. So your n equals 1 state is going to be, again, your lowest energy or ground state. N equals 2, 3, and then 4 and 5 are really close to each other. Okay, so these are drawn to scale, and as you'll notice, the energy levels get closer and closer together as you go higher and higher in values of n. All right, so that, well, once we see the equation, that'll make sense why. But again, that's an important feature of this model, is that the energy levels do get closer and closer together the higher you go. So when you have photon emission, or from an atom, so when we refer back to the hydrogen line spectrum, which had those discrete wavelengths of light that were observed, we can relate this then to an electron moving between energy levels. And so what was determined is that we had a line here at 434 nanometers. That was one of our hydrogen lines that we saw. And that corresponds to an electron going from n equals 5 to n equals 2. And that gives off light at 434 nanometers, which is observed in the line spectrum. So that we're starting here at the n equals 5 state, going down to n equals 2. So another way to draw that is on here in the energy level diagram. We have, I guess I'll just draw that as a straight line, just to make it easier. Alright, so when you go from n equals 5 to n equals 2, you give off light that has a wavelength of 434 nanometers, which is blue in color. Okay? And then if we go, we have some other possibilities here, which I'll color code. If we go from n equals 4 to n equals 2, this is a smaller energy gap. So we're going from 4 to 2 instead of 5 to 2. Smaller energy gap, which means the wavelength is going to be longer. Remember, there's an inverse relationship between energy and wavelength. And this corresponds to the line that's observed at 486 nanometers, which would be sort of a bluish-green color, so further into the green region of the spectrum. And so when an electron goes from the 4 to 2 level, that's going to give off a green photon of 486 nanometer wavelength. And then finally, the last line that's observed in the hydrogen spectrum, in the visible range anyway. So keep in mind, we're only showing the ones that are visible. You can have ultraviolet and infrared photons as well, but you don't see those. But when you go from n equals 3 to n equals 2, so even smaller energy gap now, and even longer wavelength, you get 656 nanometer photon, which is red. Okay, so when you split that hydrogen line spectrum, you can see 3 visible wavelengths, blue, sort of blue, green, and red, and they correspond to an electron moving between different energy levels, all terminating at the n equals 2 state. The emissions that terminate at the ground state are all too high in energy to see. They're still there, but they would be ultraviolet photons and not visible to your eyes, so you wouldn't see those. But you could have an electron going from, let's say, example, n equals 2 to n equals 1, but that energy gap is so large that the photon that's given off would be ultraviolet and not something that you can see with your eye. All right, so that's a pictorial representation of the model. And now let's get into the equations, which is where a lot of the problems you guys do on the homework are going to include these equations. So Bohr formulated an equation for the energy levels, which depends on the value of n, and it looks something like this. So there's a whole bunch of constants that go into this. You can derive this from, first principles. It's possible to do that, and it's based on some pretty simple physics assumptions, nothing too complicated here, except for the quantization of the energy, which is sort of the new idea. But from all this, you can derive an equation that has this form here. So you have what's called the Bohr constant sometimes, which is this minus 2.18 times 10 to the minus 18 joules. And then the energy level depends on z squared over n squared. So keep in mind here what we're doing is, because this is an interaction of a positive and a negative charge. Remember, we're talking about the energy of an electron as it's bound by a proton. Anytime you have opposite charges interacting, you're going to define the energy or the force between them as being negative. So that's why there's this negative number here. So as it turns out, n is in the denominator, which means the ground state is the most negative energy, and then as you go higher and higher up, you get closer and closer to zero. So it's all a negative scale. But the lowest energy state is still the smallest value of n, which is the most negative number. And as n goes up, it gets less and less negative until you approach zero. So it's an asymptotic relationship. It approaches zero as n goes to infinity. Okay, so this equation, the energy approaches zero as the value of n goes to infinity. So all of the bound states, the ones where you have a defined quantum number, are going to be negative energies on this way we define it. So the parameters in this equation, we have z is equal to the atomic number, just as we defined it before. So remember when we were talking about the structure of an atom, and we talked about the atomic number, which is the number of protons in the nucleus. So that goes into this equation. And then n is this quantum number that we just defined, which relates to the energy level. All right, so if you know the atomic number and you know the quantum number, you can define the energy level for that free electron in that particular quantum number. So then if we want to do a change in energy, which is important because that's related to the energy of the photon that's either absorbed or emitted, then we just have to take two values of n, compute their energy, and subtract them. And so we can get an equation for delta E, the change in energy, which is final minus initial, anytime you see that delta. And so we can simplify this. We factor out this constant, and then we just subtract 1 over the final value of n squared minus 1 over the initial value of n squared. Okay? All right, so remember the energy only changes when the value of n changes. If it's in a stable orbit, it's not going to change. But as soon as we change from one value of n to another, the energy changes, and you can compute it with this relatively simple equation. And this is one that you'll certainly use a lot. All right, and then what this equation allows us to do, and one of the reasons why the Bohr model was widely accepted early on, is because it does very accurately predict some of the key features of the hydrogen atom in particular. So with this equation, we can calculate a few parameters for the hydrogen atom. So one thing we can do is calculate the ionization energy of a hydrogen atom. So ionization, we'll talk more about this next week, but this is the process of completely removing an electron. So we take our hydrogen atom, we remove the electron, we separate it from the nucleus. So this is what's called ionization. It's the energy required to completely pull that electron away from hydrogen. And with the Bohr equation, you can calculate what this energy should be, and it very closely matches the experimentally determined values. This was one way of validating that this model was perhaps valid, is because it allows you to calculate the ionization energy. So the way that you would calculate this using the Bohr equation is when you completely remove an electron from the nucleus, you're going to the limit where n equals infinity. So you're taking it completely out of the orbit of the nucleus. So you're going to higher and higher values of n until finally you've completely removed it and n essentially equals infinity. So when your final value of n equals infinity, that corresponds to the electron being completely removed. And we can then calculate the energy that's involved in that using the Bohr equation. So we use the Bohr equation. And then we just put in the two values of n. So we have this constant out front. So when we're ionizing hydrogen, as I said, the final value of n is infinity. We're completely removing it from the orbit of the nucleus. And then if we're going all the way to if we're starting in the ground state, which is typically where you start for ionization, although you could compute ionization energies for excited states as well with some other starting value of n, but if we're starting in the ground state, the value of n is 1. So we apply this equation, and pre-calculus is a prerequisite for this course, although I realize it's not entirely enforced. But if you've taken pre-calculus, you should realize that 1 over infinity approaches 0. So this part of it goes to 0, and then we just get that constant, 2.18 times 10 to the minus 18 joules. So this number here represents the ionization energy of hydrogen, which is the energy that you have to put into hydrogen to completely remove one electron. This is per hydrogen atom, with just one single atom. And this is the experimentally determined value as well, so this model predicts that very closely. And then the other thing that this equation allows us to do is to predict the wavelengths of absorption and emission. And you can then use this equation to accurately predict where those lines show up in the hydrogen line spectrum, and that's another validation of this Bohr model that we're discussing today. So as I talked about, the energy of the photon that's absorbed or emitted is equal to the absolute value of delta E. And then we have this equation, which is the energy of the photon is equal to hc over lambda. So if you want to predict the wavelength of absorption or emission, you would use this equation, and then you would get that the wavelength is equal to h times c over the absolute value of delta E. So remember, delta E can be positive or negative depending on whether it's absorption or emission, but you should always calculate a positive wavelength for photons. There's such thing as negative nanometers. That's nonsensical. So always put the absolute value in when you're using that to calculate the wavelength or the frequency, whatever we're asking you for. All right, because delta E is going to be positive for absorption, which is low n to high n, where n is starting at some lower value and going to a higher value. It's going to be negative for emission, where you're starting at high n and going to low n. All right, but the idea here is you use the Bohr equation to calculate the difference in energy between the two levels, and then you use the equation for photon energy to calculate either the wavelength or the frequency. I suppose I could write the other piece of this equation too, which you'll sometimes use, which is h times the frequency. So if we ask you for the wavelength or the frequency, you can calculate the delta E first and then relate that to those using these equations. All right, and the Bohr model, again, accurately predicts those for hydrogen, so that was another nice feature of it. All right, we do have another caveat of the Bohr model, though, is that these equations that we just derived in this model that we've been talking about the whole time, it only applies to one electron systems. So this is the big limitation. This works great for the hydrogen atom. If you go up to helium, well, it doesn't work very well at all. So there's obviously some problems with it, and that's what we'll talk about starting next week. So we have to keep in mind that we can only use the Bohr equation when we're talking about one electron system. So the only neutral atom that's one electron is hydrogen. But the Bohr model also applies to ions that have one electron as well. So if we had the helium plus one ion, helium has 2 electrons, you take 1 electron away, it's now left with 1 electron. Lithium 2 plus would only have 1 electron, beryllium 3 plus, and so on. And these are not all stable, observable ions, but the equations do apply to them. So these have different numbers of protons in the nucleus, and that's where that Z term comes into play in the equation, the atomic number term. But the equation only works if there's only a single electron that's orbiting that nucleus, which would only count for hydrogen and then these ions, and you could go higher and higher if you wanted to, but it's anything that has 1 electron, where we removed all of the electrons but 1. Okay? So we have a little bit of time for some sample questions now, which will take us through most of the rest of what we're going to talk about today. All right, so let's see the first one. True or false? Minus 6.36 times 10 to the minus 19 joules is an allowed energy level for a lithium 2 plus ion. Okay? So we're giving you the energy level, and we want to find out if this is an allowed energy level for the system. Now, we're not talking about a change in energy here. We're just talking about the energy of an electron bound to the nucleus. We have this equation for that. All right, so basically what we want to do in this is we want to solve for n. We want to figure out what's the value of n when it has this value of the energy and see if that's a valid value for the quantum number n. Remember that n has to be an integer. So if this corresponds to a value of n that's an integer value, this is going to be an allowed energy level. If this corresponds to a value of n that's non-integer, that means it's not an energy level that can exist for that atom. Remember that we can only have those discrete energy values that correspond to n equals 1, 2, 3, 4, and so on. We can't have n equals 3.3 or n equals 2.7 or anything like that. Okay, so we're going to solve for the value of n. Now we need the value of z to be able to do this. Remember that z is the atomic number. I didn't give it to you here, but as I talked about last time, we can get that from the periodic table. I really wish this room had one, so I'll have to pull mine up. Alright, so we find lithium on the periodic table. It's over here, and the number there is a 3. So that means there are 3 protons in a lithium nucleus. So that's going to be the value of z that we use. This is a 1-electron system, which is the only time when we can use the Bohr equations. Lithium 2+ only has 1 electron left. And now we're going to solve for the value of n using some algebra. So we put in the energy value, minus 6.36 times 10 to the minus 19 joules. And that's going to be equal to this constant, minus 2.18 times 10 to the minus 18 times z squared, which is 3 squared, divided by n squared. Alright, so all we have to do is solve for n and see if this is an integer value or non-integer value. That will tell us whether the energy level is allowed or not. So we're going to do some algebra. I'm not going to do it for you. You're welcome to try this on your own. So I will sometimes do this to save time. I'll just wave my magic algebra wand and skip a bunch of steps. But this is not an algebra course, so I'm confident you can all do this. So when we solve for n squared, we get n squared is equal to 30.85 or somewhere thereabouts. We take the square root of that to get n. And you can probably already recognize that this is a non-integer value. 5.55 is the actual number we get. Okay, so that means that this is false. This is not an allowed energy level for lithium 2+ ion because n must be an integer. Alright, if we were in some alternative universe where n could be whatever we wanted it to be, sure, this could work. But in the present state of the world that we're in right now, n has to be an integer value, 1, 2, 3, 4, 5, and so on. This is between two integer values, 5 and 6, so that would not be a stationary state or an allowed energy level for that ion. Alright, so that's an example of how we use just that simple equation to say something about the energy levels. Let's go on to some other ones. Alright, so now we're going to do a very classic problem where we have to determine the energy and wavelength of light emitted when hydrogen jumps from the second orbit to the ground state. So we're talking about emission here, which is going from higher energy to lower energy value. And so when we read the problem, we know that we're going to be automatically using this equation. Anytime we're talking about energy of light that's emitted or absorbed, we want to use the Bohr equation. So often it's helpful to write out the equation that you know you're going to be using and then figure out which terms you need to be able to solve that. So we know that this depends on z squared, and it also depends on the two values of n, the final value of n and the initial value of n. Okay, so we need 3 terms to be able to calculate delta E. We need z, which is the atomic number, and hopefully without looking at the periodic table, we realize that z equals 1 for hydrogen. Okay, so it only has 1 proton. That's the first element in the periodic table. That should be familiar, but you can go to the periodic table if you didn't remember that. And it's the first element there. And then we also need the 2 values of n. So it's jumping from the second orbit. That's your initial value of n. That's where it's starting. And then we don't give you the second value of n, but we give you a clue about that, the ground state. So anytime you see the word ground state, remember that means something very specific about the value of n, which is that it equals to 1. So our final value of n, where we're ending up, is 1. Okay, so those are the 2 values of n we're going to put into this equation, and that's going to allow us to calculate the energy difference between the two, and then we can use that to calculate the wavelength, which is the second part of this. Alright, so when we put those values in, we get one over 1 squared is the final value, 1 over 2 squared is the initial value. So our change in energy is going to be negative because it's emission. We get minus 1.64 times 10 to the minus 18 joules. So that's the energy difference between the n equals 2 state and the ground state. Now we should keep something in mind here. We don't want to get too hung up on the sign here. If you switch the values of n, all that's going to happen is you're going to have the wrong sign, which if you're just calculating the wavelength or the frequency, it doesn't matter because that's always going to be a positive number. if we're asking you, though, for delta E, you need to make sure you have the sign correct. Remember that the change in energy can be either positive or negative. So that's where it's important to keep in mind whether you're doing absorption or emission and make sure that you get the correct sign. But if you switch the two values of N in the equation, you'll just get the opposite sign. You won't get the wrong number or anything. All right, so now we need the energy and the wavelength of the photon. So the energy of the photon, as we've talked about, is just equal to the absolute value of delta E. So when we go from the n equals 2 to the n equals 1 state, our energy changes by this much, and then a photon that has that same amount of energy is going to be emitted, and that's what we observe. So we get the energy of the photon is 1.64 times 10 to the minus 18 joules. And then once we have the energy of the photon, we can relate it to the frequency or the wavelength. So if we want to calculate wavelength here, that's going to be h times c divided by the energy of the photon, just rearranging the equation for energy that we talked about and introduced last time. And so when we do this, we put the value of h and c in, which is going to be on your list of constants if you don't remember it. 6.626 times 10 to the minus 34 joule seconds for h. Speed of light is 3 times 10 to the 8th meters per second. And then we put that over the energy of our photon that we calculated, 1.64 times 10 to the minus 18 joules. So if we want to check units, joules cancels, seconds cancels, and we're given a wavelength in meters. 1.21 times 10 to the minus 7 meters. I didn't specify units in this problem, but it's more conventional to report wavelengths of photons in nanometers usually, especially for things that are close to the visible spectrum. So we get 121 nanometers if you just multiply that by 10 to the 9. All right, and if you remember what I talked about last time, the visible spectrum, the spectrum of light that we can see, starts at about 400 nanometers. And this is way below that, so this would be considered ultraviolet radiation. So that's why this n equals 2 to n equals 1 line is not one that we can actually see in hydrogen, although it certainly is there. And if we have an ultraviolet detector, we can observe light at 121 nanometers that corresponds to the emission from the n equals 2 to the ground state. Okay? All right, let's do one more like this. Actually, let's do this one real quick. Okay, so this one is very similar, but here we're talking about a lithium 2+ ion, and as we talked about earlier, that means Z equals 3. So this is an identical problem, atom going from the second orbit to the ground state, n equals 2 to n equals 1, but this time there's 3 protons in the nucleus instead of 1. So let's see how that influences the energy and the wavelength of the photon. So we're only perturbing the nucleus in this case. So the change in energy using that same equation. So we'll go through this one kind of quickly because it's a very similar problem, but remember we have this term here, Z, for the atomic number, which we can't forget about when we're talking about things other than hydrogen. So for hydrogen, Z is 1, but in this case is 3. And then we have the same values of N. Our final value of N is 1, so we're going to the ground state. Our initial value of N is 2, which is where we're starting. And so when we calculate this out, we get minus 1.47 times 10 to the minus 17 joules. So about an order of magnitude larger. So the difference in energy between n equals 2 and n equals 1 is larger when you have more protons in the nucleus. That's what this will tell us here if we compare this to the previous one we did. The energy of the photon, of course, is the same as before, just the absolute value of the change in energy. And then we use the equation lambda equals hc divided by the energy of the photon to get the wavelength. So hc divided by so those are those constants. I'm not going to write them down again. And we get 1.35 times 10 to the minus 8 meters, which if we put that in nanometers is 13.5. All right, so when you go, and this comes straight out of this equation here, when you add more protons to the nucleus, the energy gap between the levels gets larger, which means that the wavelength corresponding to that would get smaller because of that inverse relationship. So here we have a larger energy spacing and a smaller wavelength for the exact same n equals 2 to n equals 1 transition, because now we have 2 additional protons in the nucleus. All right, so those two give you an idea of a pretty standard problem that we would do for these. All right, let's do one more, which is, again, same equation, but just a little bit different in terms of what we're solving for, a little bit different algebra in this case. So a bunch of these atomic lines in hydrogen are named after different people. So the Paschen series is one that involves transitions that terminate at the n equals 3 level. Okay, so if we start at some higher value of n and we end up at n equals 3, that's called the Paschen series. So for lithium 2 plus, a Paschen line is observed at 1424 angstroms. Now I believe this is introduced in the review chapter, but I should give it to you here. This symbol here, A with a circle above it, is a unit called angstroms. It's not the most common, but it is sometimes used because it's on the atomic scale that we're working with in chemistry. So it's equal to 10 to the minus 10 meters. Okay, so this is just one order of magnitude smaller than a nanometer, basically. Okay, so that's another unit you may want to be familiar with. I think we'll define it if we give it to you on the test, but just in case, it's 10 to the minus 10. I believe that's covered in the review chapter. Okay, so in this case, we have a Paschen line for lithium observed at 1424 angstroms. We want to know which level did the transition originate. So again, it's going from a higher value of n to n equals 3. What's the value of n that it started at to give off a photon that has a wavelength of 1424 angstroms? All right, so if we do this, we want to first find the energy of the photon that this corresponds to. So the energy of the photon is equal to the absolute value of the change in energy for the atom, and that's going to be equal to hc over lambda. All right, so we put 6.626 times 10 to the minus 34. So the first thing we're going to do in this problem is calculate the energy of the photon, which is then going to be related to the energy difference that the atom undergoes when it does this transition. So we're kind of working backwards in this case. I'm giving you the wavelength, and we're going to now calculate the energy difference and use that later on. All right, so we need to put the lambda down here. Now remember, when we're using this equation with the speed of light in meters per second, our wavelength has to be in meters. So we want to convert this 1424 angstroms, this weird unit, into meters. We have to divide by 10 to the 10th. So it's 1.424 times 10 to the minus 7 meters. Okay, so that's the value that's going to go here in the denominator. So as I warned you about last time, don't forget about units when you're using these equations. And so we get 1.40 times 10 to the minus 18 joules. All right, so this is the energy of the photon that's given off, and that's related to the absolute value of the change in energy. Now what we should realize is that this is where the sign does matter, and emission is dealing with the process of going from higher value of n to lower value of n, which means that our change in energy is going to be positive or negative. Higher to lower, so it's going to be, try the other one, negative. So remember, it's coming down in energy, it's losing energy, it's getting lower in energy, so the final state is lower than the higher state, so you subtract the two, it's a negative number. So anytime you have emission, delta E is negative, going from higher energy to lower energy, which means that the delta E for this process is just the negative of that, minus 1.40 times 10 to the minus 18 joules. Because if we're going to use the Bohr equation to find the value of n that this corresponds to, we have to also make sure that we have the correct sign. So once we do this, we use the Bohr equation. Delta E is minus 1.40 times 10 to the minus 18 joules, and that's going to be equal to this constant, the Bohr constant, times z squared. We're talking about lithium 2 plus again, so z is 3. And then it's going to be 1 over nf squared. And as I told you here, this is the Paschen series, so the final value of n is 3. Terminates at the third energy level, so that's our final value of n. And then we're solving for the initial value of n. Where did the electron start before giving off this photon at 1424 angstroms? All right, again, we're going to bust out the old algebra machine. We get the initial value of n squared is equal to 25, which means the initial value is 5. So if you do a problem like this and you get something that's non-integer, you definitely want to check your work, because as I said, all values of n have to be integers. So when we solve this equation for the unknown value of n, we get a value of 5. So to recap what we did, we used the wavelength of the photon to calculate its energy. That's related to the change in energy for the atom. And then using the Bohr equation, we can solve for the unknown value of n. All right, let's move on. Let's try the clicker system one more time to close out today. So I didn't hear about any problems last time, but I'll test it again to make sure that everything's working properly. So again, this one won't count for anything, but if you have your clicker, please get it out and give this a try. I forgot to do something again. We're going to have to start a setting. I'll figure this out eventually, don't worry. Alright, so still channel 47, a new session ID if you're using your phone, and I will start the timer in a second here. Alright, so again, this is a good chance to try one of these problems and see how you do, but most important thing, enter an answer so we can at least test the clicker system if nothing else. But alright, so we already have a lot of responses, which means you're either really fast or really apathetic on a Friday afternoon. Again, this one doesn't count, but do give it your best shot if you have the desire to do so. Alright, about a minute left to get an answer in if you desire. Alright, again, please let me know if you have any problems with your clicker. We want to get this sorted out in case we have a real quiz soon. 30 seconds. Okay, time's up. Let's see how we did. Alright, so 57% had A, and then the next popular choice was B. So let's go back and work this through just really quickly before we close out. Oh, come on. Alright, here we go. Alright, so the way we're going to do this problem is we're just going to apply the Bohr equation twice, one for this hydrogen atom and one for helium plus. Alright, so the Bohr equation, delta E, so really a straightforward application of this equation. I want you to learn this one because you're going to use it a lot, and we don't give you equations on the test typically. So for hydrogen we have a Z of 1, this is the Z term. And then we're talking about n equals 1 to n equals 3. So the final value of n is 3. The initial value is 1. And so for hydrogen, we get 1.94 times 10 to the minus 18. Now, we're talking about the energy of the photon, so all that really matters is the magnitude of this, but it should be a positive number because we're going from lower n to higher n. 1.94 times 10 to the minus 18. We do the same thing for helium, same equation, but we have a couple differences now. The value of Z for helium is now 2. Helium is the second element on the periodic table, it has 2 protons in the nucleus. And then this time we're talking about n equals 2 to n equals 4, so the values of n are going to be 4 and 2, which we're going to subtract the inverse squares of those. And this time we get 1.64 times 10 to the minus 18. Okay, so we're looking for the higher energy photon, so the one that's higher energy by a little bit is hydrogen, which means this time we did much better, and most of us had the correct answer, which is A. Alright, so again, if you had any problems with the clickers, try to get it sorted out or let me know, and I will see you on Monday.
There's a big periodic table right behind that screen.
Yeah, if I raise the screen, people on this side are going to have a real problem seeing the screen.
I just wanted to ask, is